So hi everyone and welcome to this week's Crunch seminar. This week too we have two speakers. Our first speaker is Yiping Lu. He would be presenting today on a topic titled Machine Learning for Numerical PDE, Fast Rate Neural Scaling Law. A little bit about him. Yiping Lu is a third-year PhD student at Stanford University working with Lexin Zing and Jose Blanchett. He received his bachelor's in computational maths from Peking University in 2019, where he worked with Professor Bin Dong and Liwei Wang on scientific machine learning and machine learning theory. His research interest lies in machine learning for physics, ordinary differential equations and stochastic differential equations, limits of residual network, machine learning under distribution shift, and causal inference. With that, Yiping, I leave the stage for you. So thank you. You may want to start.
Yeah, okay, thank you. Okay, sure. So today I will talk about machine learning for numerical PDEs. Fast rate is like saying that I will give some very fast generalization bound and convergence bound. And what's the neural scaling law? I will not talk about too much today, but it's a very interesting topic in like deep learning community. It is saying that I want to know what's the convergence rate of the generalization loss respected to the number of data I have, and I will tell you that our bound is optimal. Yes, so I think I doesn't need to emphasize that the machine learning for physics is important and interesting here, and everybody now is like trying to combine like using physics and using machine learning to solve problems today, and everybody is telling about is discussion about this, but I think there is very less discussion about if I use physics, if I use some physics knowledge, how many data I need, so how many benefit I need. As an example, previously I need a lot of data. Everybody saying that if I use some physics now, I can use some less observational data, but it is all like experimental result, but nobody tells me that how much data I can actually reduce. So I want to answer this question in this talk. So here are the three main questions I want to answer today. The first question I want to answer is the statistical limit. So for a given PDE, I want to solve it. How large of the number of data I need to reach a very good performance level? This is the first question, like statistical limit. So in this question, I doesn't consider any estimators. You can be any estimator. So it is like a lower bound doesn't depend on the algorithm. And can we construct a model that can achieve this statistical limit? This is the second question. So I think these two questions is answered in our paper published have submitted to arXiv recently, and in this talk I also answer the third question. It's about computational power. Can we design an algorithm like the stochastic gradient descent? Can some computational algorithm achieve this statistical limit? This is our ongoing work, and I will talk about it today. So these are the three main questions I want to answer in this talk. So let's first talk about some problem formulation, and then go to the lower bound and upper bound part. So the problem formulation. So to simplify the problem, like just to solve these very simple equations, or you can just consider the equation here is the simplest Laplace equation, and with the zero boundary condition. So the question I want to ask is that I can observe some random observations of f. Okay, this is the only thing I can get, is like some random observation of f, and I want to estimate the function u. So I have random observation of f, and I want to estimate the function u here. So how many data I need? So how many samples it can give you enough information to like I can know what's my u in epsilon accuracy? This is the question I want to ask first. So before we go through the lower bound, let me first tell you very fast the algorithm I'm interested. The first one is the physics informed neural network is like I'm minimizing the residue directly. And for the second algorithm I'm interested in is the deep freeze method. So different from the PIN, the deep freeze method using the RIS form. So it can't work for every PDEs. It just works for several PDEs. So if the PDE have a variational form, I can use the variational form. So there is a very nature question is like, okay, the deep freeze method can't like PIN works for every PDEs. Does it have some benefit? I think this is the first sort of, this is the first motivation of this research. But actually goes down, I will answer this question. But at this time, let's forget about the algorithms. So I want to tell you the lower bound, but for the lower bound, why I still need write down these two equations is because I would like to say something about the norm here. So for the PIN, the norm here is you can consider the norm is actually if I have a U and the true solution is U star. So this loss function is approximately the H2 norm. Okay. Right? So because I have two gradients here. And for the norm here, it's approximately the H1 norm. If I'm using a machine learning algorithm, I'm using H2 norm as my loss. If I have some generalization bound, you can imagine that I can just have guarantees here and H1 guarantees here. So for the lower bound for these two problems, they are very different. So for the lower bound, I proved for PIN, I will interested for evaluating my solutions in H2 norm. But if I want to prove lower bound for deep freeze method, I will need the bound here to be H1 norm. So here is the difference. So for the lower bound, I will first show you the algorithm, and I will tell you about the intuition behind the lower bound. So for the lower bound, what it is saying is that if I have the information is the data sampled from noisy observations of the right-hand side function f. Let's remember Laplace u equals f, and I just have random sample of it. So any estimator means that the h is a function. H is a function from these n datas mappings to a function in H1. So I have any functions, H can be any function, takes n data in and outputs a H1 function. So for every H, what I can prove is that in expectation, the estimators will have error at this error. Okay, so it looks complicated, but no worry, I will tell you about how I understand it. So for the setting, I will always say that the lower bound should work for a class. The lower bound should work for a class of function, but not like a single equation. It's because if I just consider Laplace u equals to f, I can't give such lower bound. I can always let my h output f. So if I want to have the lower bound, I always need to consider a class of problems. As an example, I have a class of problems, and you can't let your estimator h just output the right solutions. So they maybe have some problems very similar. I need to discretize them. So this is the part why I need this supermer here. And for the infimum here, it is saying that my h is the best estimators. Okay, this is the minimax part. It is saying that I want my estimator works uniformly good for a class of function. And for a class of function, it is in a Sobolev space. So here is C, here is H, but I will tell you that no matter H or C, the lower bound is the same. Okay, so it is like I need my U function here to have alpha gradients. Then you will have a lower bound like this. Okay,
I have a question.
Yeah.
I have a question.
Yes.
So for 2 dimensions, your lower bound doesn't depend on regularity. Is that right?
Oh, what do you mean by the regularity? I think the regularity comes about like the U here.
I know, but look, if you take D equals 2,
yes,
then this becomes 1 over n on the right hand side. So the right hand side doesn't depend on how smooth the solution is. The lower bound. Your lower bound is a special case. The lower bound does not depend, and that's kind of odd. Why just in 2 dimensions?
Okay, yes, that is a good question.
I want a good answer. I want a good answer. Why?
Yeah, this is a very good question. I need to consider about this for a while. I can tell us about the proof. Let's see what happens for during the proof. Yeah. So yeah, I don't know. So it doesn't happen for estimating a function. So if my function is in H alpha, I gives you some. I want to estimate it, and I gives you directly like it's the value of u. The bound is here will looks like this.
Yeah. So
Yeah,
it's
it will.
a little odd. Yeah.
Yes, it doesn't happen for the problems here. Yes,
That's right. 1D or 3D or just in 2D only, you have this problem. So I wonder why is that? I mean, there must be some assumption that because there's no particular reason. The 2D is not any particular sampling. I mean, it would come from sampling. Yeah. Anyway, that's something to consider.
Yes, thank you. Yeah, I will consider this problem. So yes, for d equals to 2, it's always a constant, right? Yeah, but it's not the case for estimating a function. So for estimating a function, you will always have a rate depend on your d and alpha. You can't like a magic cancel here. Yeah, thank you. Yeah, I will consider this. Yeah, and for the lower bound, I will tell you about why I have this -4 and -2 here, and let's see why d equals to 2 may be special. So for the lower bound here, or how I get this lower bound is like I want to solving a PDE problem into a classification problem. So the idea is here. So if I can solve PDE epsilon accurate, that's if I can solve it epsilon accurate. So I have two PDEs. The one PDE is like U1 and U2. Their distance is larger than 2 epsilon. And I give you some data sample from here. If I can solve it epsilon accurate, I can tell you the data is from U1 or U2, right? I can do a classification problem. The classification problem is that I give you Xi and Fi, and you need to tell me it is the data is sampled from the PDE U1 or the PDE U2, right? You can answer me this question. So otherwise you can't solve it very clearly. So in this intuition, you can turn solving a PDE into a classification problem. I give you several PDEs, and all of their solutions is separated by some epsilon. And then I give you a data set. The data set is sampled from one of the PDEs, and you need to have the information enough to tell me which data it is sampled from. So this is like turning a estimation problem into a testing problem in standard statistics. So in this case, then I can tell you that how much information you can get. The information is like the Xi and Fi is sampled from your data, from different problems. So you can bound their KL divergence. The KL divergence will tell you how much information you get in your hand. So then we can use some information theoretical tools to give you the lower bound. Okay, so now I will introduce the class of problems I'm considering. So it is like here are the hypothesis functions. I have different U case, and I give you the data from U case. You need to tell me which data it comes from, which U case it comes from. So the hypothesis here is actually very simple. It is saying that I just divided my space into different grids, and I add a bound function onto some of the grids. Okay, so it is like it's some grids, and I add a bound function into some of the grids, and for while each time I add a bound function, the m here is the grid size, so this is m1 over m. So each time I add a grid function, add this bound function, I need this normalization factor here. The normalization factor here is to let your U have some regularity, right? So this is what happens here. This is the hypothesis class I'm considering. And now I need to consider two problems. The first problem is what's the difference of the PDE? It is like how they are separated. So in this case, you need to bound the sorbolic norm of U. And the second question is like, how are the data similar to each other? If the data are similar to each other, then you will have like very hard to classify if they are very similar. Their KL divergence are very slow, but they are from two problems. You need to classify them, then it's very hard. If the KL divergence is very fast, then you can classify them very easily. So it is like you need to bound two quantity. The first one is the similarity of the data, and the second one is the difference of the PDE. So for the difference of PDE, it's very easy. It's just like the sorbolic norm you are interested. For PIN, it's like H2 norm, and for DRM, it's H1 norm. But for the data, what is the KL divergence? So you can consider our data is sampled actually from the right-hand side function f, right? Laplace u equals to f. You are sampling your f from your right-hand side function. So you can imagine the KL divergence will just similar to the L2 norm difference of your f. So what is this saying? The L2 norm of your f is actually the H2 norm. Right? It's because your f is actually, you take two gradients of your u. And for the sorbolic norm here, you are interested, it is like for P is H2 norm. And for the DRM, it's H1 norm. So you can imagine if you are PIN, your two norms here is actually matches. If you're, so that's what happens. So for
You're not audible sometimes.
Sorry?
You were not audible for some time, for 2-3 seconds.
Oh, sure. Okay. Maybe the internet problem. Is it working now?
Yes.
Okay, sure. So this estimating function, the convergence rate is something like this. And for estimating P, the lower bound will look like this. So you can see the difference here. The difference here is actually you just takes out two gradients. The difference is like if you want to prove the lower bound for estimation function, all the two norms here is L2 norm. For PIN, the difference is that you're replacing the norm here from L2 norm to H2 norm. So you just remove two gradients. So you just remove two gradients in your bounds, and you'll get something like this. And for the DRM, there is only another very slight difference is to change the change the H2 norm to H1 norm. So there is only difference is like I will replace the -4 here to -2. So this is how the lower bound comes out, and this sense, I can give you some very general lower bound, although I doesn't write it down in the paper because I can't have very precise formulation of it, but you can consider this is what happens. If you have a teeth order PDE, like I give you the PDE like gradient, use teeth gradient equals to some function. This is your PDE, and I assume you have regularity, and I consider the convergence in HS norm. So the difference from estimation function, the rate d plus 2 alpha over 2 alpha, the only difference is here. If you are teeth order PDE, then you -2t here. So if you are if you are HS norms, then you have a -2s here. So this is the only difference here. So for the PIN, it's a very good thing. It's like it looks like fitting a function. So the S and the T here will matches. So you are just matches the T and S here. So it will look very similar to the estimating a function rate. So yes, that's a very good question for decrease method. So if you take the Laplacian equation here, if you take d equals to 2, it goes to a very magic rate, and it should be something very special happen here. I need to check. Yeah. So for this lower bound I have here, do you have any questions?
Hello, this is Lulu from Japan. So I have one question.
Yeah.
So what if we also consider we have the information of the boundary condition or initial condition? Will this lower bound be increased? or be
Yes,
improved?
yes, this is a very good question. Actually, we can do the boundary condition. So, but we doesn't write it down in the papers because for the upper bound, we can't match the lower bound. So if you are these linear equations, it's very easy. So if you consider my equation is just Laplace u equals to f, and I have a boundary condition here, right? So in this case, you can actually separate it. I first solve an equation. It is like Laplace u equals to f and have zero boundary condition. And another one is just solves Laplace equals to 0, and I have a boundary condition. So you can imagine the lower bound here in the domain, it doesn't changes, right? So I just need to have another lower bound for this problem, right? So for the lower bound,
yes.
you can have very similar proof and you can prove it. But I can tell you, so although it happens for the upper bound, why we doesn't write it down in our paper is that if we need to write the upper bound, you can imagine, because I'm a boundary condition, I will need some sort of embedding theorem. So I will need to estimate a function in h like h half norm, something like this. And in this case, I can't give a very optimal upper bound.
Okay, thank you.
Yeah. So it's for the upper bound. So for the lower bound, you can do all the same thing. But for the upper bound, I can't say it becomes optimal. We are still working on it. Yeah. Thank you for the question. Yeah. Okay. So then I'll go to, yeah. Yes.
I have a question. So this is for over all U, right? This is
Yeah.
in max bound. Do you have things like parameter bounds or something that depend on U? Because it might be that for worst case use you get this rate, but then on average you use
Yes, these are very good question, but it's very hard to answer because it's a very fundamental question for use. So I have told you that I can't consider only one U. I should consider like a class of U. Otherwise, the lower bound doesn't hold. So I think there are some literature in statistics saying that I want to localize U because maybe some of the U is hard. So they want to prove that the lower to the lower bound is like a neighborhood of it. Neighborhood of it and the neighborhood ratio, the neighborhood radius r here, they will select to something like 1 over square root of n. So there are some lower bounds here. But I would like to mention for all these lower bounds, they always give all these kind of lower bound for parametric problems. But here I'm on non-parametric problems. It's very hard to build this kind of bound. So I think this is the only thing I know for non-parametric estimation. I can build a lower bound. So it's a very fundamental question in statistics. Yeah, I must have this class, but you can localize your class, but for localizing the class, it's very hard for the non-parametric problems. Yeah.
Thank you.
Yeah, so now I will go to the upper bound part. So for the upper bound part, I think there are many good papers, including some paper from your group. So I have some previous bound for the problem, but I will tell you why the previous upper bounds are not tight for this problem and how we improve it. So for all the previous bounds, the idea here is based on this bias and variance decomposition. What's the bias and variance decomposition? I will tell you very fast. It's like, okay, so let's consider U star. U star here is the solution of my PDE. It lies something here, and I gives you a class of parameterized functions. It is like the gray circle. So it is like all the neural network I have or some kernel functions I have. So this is the gray circle. So the first thing is the approximation error, or it is called bias. You can think that, okay, my U star may not lie in this gray circle. So I need to find out the one that approximates best of this solution. Okay, so this is the first error. And for the second error is that, okay, I'm saying that it's an approximation good. It is like in expectation is the approximation is good, but actually what I can get is actually en. So what's en here is like the expectation over empirical data. So I still have a distance from the empirical data to the approximation error. So this one is called generalization error. So everyone will suspect is that or in most of the applications, the generalization error here is 1 over square root of n due to the chain of bound. So if you go through this machine learning literature, you will get approximation bound and plus a square root of n over complexity bound. So this is the bias and variance composition, and several papers have do this for both PIN and the DRM. So this story sounds good, but if you go through this bound, especially the Duan paper, you will find out that the bound here will not give you the optimal solution. So what's wrong here? So for what's wrong, I will first give you a very motivating example. It's very simple, but the proof here doesn't hold for like neural network for this problem. So let's just have some motivation here. So the motivation here is I want to estimate a mean. So to estimate a mean, I can use the loss function like the L2 loss function. So the empirical version of this loss, the solution here is just the empirical mean. So using trade-off bound, what I know is that the empirical mean, the convergence from empirical mean to the mean is square root of n. But I'm using the L2 loss. So if you consider the generalization gap, your loss function. So your loss function is actually the square of your true loss. Like the true difference. So here you have a square. So what you can prove is that your loss function here is actually converges in 1 over n. So for your loss function is a 1 over n convergence. So let's consider what the previous paper do is that, okay, let's do concentration bound on L. Because on L, you can also write it down as some expectation, right? So let's do the concentration on L. So for the previous paper, what they have proved is actually for the L functions, they have a 1 over square root of n convergence. So if you consider the theta, they are very slow convergence rate. So this is what happens if you are using a square-like loss. If you are using a square-like loss, you can actually have a fast rate generalization bound called 1 over n fast rate generalization bound. This is what happens just because your loss is square. This is also happened for our problem, because like for the PIN, you are square, right? You write down your L2 norm square. And for the deep risk method, the risk form itself is actually behaves like your H1 norm square. So the variational form here has some strong convexity. We should assume that the generalization bound here, if it is a linear problem, you can easily prove that it is 1 over n generalization bound, but not 1 over square root of n. So is this the case here for neural network? For neural network, can we prove some of this 1 over n generalization bounds? The answer is yes. So it is a long literature for using neural network to non-parametrically estimating a function. So for approximate, as an example, like for Sobolev function or Holder functions, if you want to use neural network to approximate it, the approximation bound is always looks like this. This is the approximation bound, and the D is the dimension, and S is the regularity. Okay, so this is your approximation bound, and n is the number of weights, of the weights of your neural network. Okay, so if you have once you have a 1 over n generalization bound, if I write down the 1 over n generalization bound like here, and if you minimize this, you will find out this will lead to a 1 over D plus 2s over 2s convergence rate. So this is how it happens. Oh, sorry, I have a 2. I missed a 2 here. So yeah, so here is 2s. Sorry, I missed a 2 here. So this is how you get the optimal rate for non-parametric estimating a function. So the takeout is that if you want your rate to become optimal, you need this 1 over n fast rate generalization bound. So how this paper achieve this? They are using so if I'm using a neural network, the only thing I can do to bound the generalization bound is using the random complexity. And once you use the random complexity, you will get the 1 over the square root of 1 over n rate, right? You will always have this slow rate. How can I jump from this slow rate to the fast rate? The idea here is actually very simple. It is called local random numerical complexity. I need to consider my random numerical complexity not in the whole space, but in a localized set. What is the localized set here? The localized set is actually the U star is your true solution. And you can imagine if I have enough data, my true solution will become very near to my true solution, right? So U hat is the solution I estimated. It should be very near to the U star. So I can imagine that the U hat lies in a ball centered at U star and with radius r. Let's imagine my U hat lies in this ball. Okay, so I can do the local random numerical complexity. I just do the random numerical complexity of this red ball. For this red ball, if you write down the random numerical complexity, it's still square root of 1 over n. Okay, but you have a dependency of it over r here. Okay, and this is the first thing. So what is this generalization bound saying? It is actually bounding the difference of em minus e in this ball. And you can imagine this difference is also you can have a bound like this difference is also some difference between U hat and the U star's distance, right? So this will also bound something like this. So here is H no. So you can imagine this thing will approximately to R. So once you solve this equation, then you can get the R will equals to 1 over n, and you get the fast rate generalization bound. Okay, so to be short, so if you want to have this optimal rate, what you should consider is not the random numerical complexity, but it is the fixed point solution of this local random numerical complexity, like the phi r equals to r. And if if your function have like some square-like behavior near the solution U star, then you will have this equation like the square root of r over n equals to r, and this equation can give you the solution of 1 over n. Okay, so what it is saying is that you have if you have a unit, okay, the operator convergence of E minus En, the expectation convergence here is still 1 over square root of m, but the solution convergence is actually not this rate. The solution convergence is actually you can have a faster rate using this localized trick. So what I tell you is actually the simplest version of this localization, but actually you can go through like the literature here to see how different localization ways to be done. What I can tell you is that like all these methods, they have very, you should be careful about the hidden assumptions. As example, this thing I do here, you need like the convexity of your empirical loss. Convexity means I doesn't consider the neural network. It is like the convexity of the loss function, just the loss function, but not the function you plug in. The loss function itself should be a convex function. It's true for Ping and the Diepries method without boundary condition, but with boundary condition, this assumption doesn't hold. So you should choose a right way to do the localization. And for the localizations, they always need an assumption that all the random variables are bounded except for the paper 4 and the paper 5. So for the way I do this localization, I also do these assumptions. But I think for most of the applications in physics, you can't do such assumptions. So if you want to use this method for your physics problem, you should be very careful to the hidden assumptions. So like for different methods, they should work for different problems. It's not like I have like these very simple ways I can do all of the problems because they all have very subtle hidden assumptions. So if I use this fast rate, am I optimal? This is the question I want to ask, and I do some calculations, and it comes out these tables. You can see the Ping is actually optimal, but the Diepries method doesn't. So the difference here is also very subtle. You can see for the Diepries method, if you go through all these bounds, you will always get some rate like this. So these two things are the same, but you know for Diepries method they shouldn't be the same. This one is still looks very similar to the function estimation rate. So this is what we get from the this is what we get from the from the fast rate generalization bound, and I want to know why the decrease method is not optimal. So there are two possibilities. One possibility is that my math is not good. I can't bound it very tightly, right? And the second answer may be the decrease method itself is not very good. So to answer this question, I want to go through the Fourier basis. So once I plug in a Fourier basis, all the problems will become linear problem, and I can solve it in closed form solutions. And also kernel is very useful for some of the problems in high dimension if you know some structure of it. Like here are two papers saying that in high dimension for some quantum physics papers, if you know the structure of your ground truth solution, then you can build a very some very kind of tensor tree formats, and you can do better. So that's another motivation why I want to use kernel as an example. Okay, so let's consider I have this very simple PDE Laplace U equals to F, and I want to solve it using kernels. So to estimate it, I actually have two ways to estimate it. The first way is using decrease method. And the second way I want to estimate it is that, okay, I want to solve this equation. I doesn't consider computational, I don't consider any computational resource problems. So I can estimate my F, right? I can first use using Fourier basis and estimate my F. And then I directly solve this equation. Okay, I directly solve this equation. If I have infinitely many computational power, I can do this. And you can imagine this one, it should be optimal if you estimate your F in H-1 norm. So this is the tricky part. If you estimate your F in H-1 norm optimally, then you can do all the things, right? You can inverse your equation and do all the things. So this is the first estimator. The first estimator is that I estimate my F, and I directly inverse my function, right? I directly inverse my Laplacian here. So this is estimator one. So I need to emphasize again is that the estimator one is not an algorithm. So the estimator one is just like experiment. It's just like an experiment. I want to show why the decrease method is not good. It's just for the output. And for estimator two is that, okay, you can parameterize your U using your Fourier basis, and you plug it in your decrease objective function, and then you write it down. You can see this objective function itself is actually a quadratic function, so you can write down the solution in closed form. So let's see what happens. So it's in quadratic form, so it's always some function looks like always like some matrix inverse of your Fourier coefficient. So what's FC is the Fourier coefficients of your F. So it's always some matrix inverse yet. For the estimator one, you are inverse yet directly. So you will have these two coefficients here. Okay, some diagonal matrix of like from 1 to z squared. Okay, for the estimator two, you plug in this into a decreased objective function, and what you'll get is actually you are not getting this two matrix here. You are getting a approximate version of it, and the approximation is the sample from the random data. So in expectation, the grand matrix of the gradients of your Fourier basis is this one. But now, because you are decrease method, you can imagine what you have for this term. You approximate it by n data, right? You approximate it by n data. So the matrix here is an empirical version of it. And if you do some calculations, you will find out that the matrix, like the grand matrix convergence, is actually some kind of slope. Okay, and this rate will dominate its convergence of your estimator one. So that's why the decrease method is not so optimal, and we can improve it very, very simple. So how we can improve it is that, okay, why we know why it's some slow is because this empirical grand matrix converges slower. So I can use more data to calculate my grand matrix, right? So my grand matrix here doesn't need my F's information. The grand matrix here, I only need to sample more X. It's doable, right? It's doable because it doesn't require more F. So if you write down your objective function, you can see for your gradient term, For your gradient term here, gradient square this term, it doesn't have any f involved, so you can sample more. So if you sample more, you can write down your also you can write down all your bounds, and you will find out that how many more gradients you need to sample. It will go to some quantity like this. So if your D and S is large, this term is actually very small. So it's like in high dimensions, smooth functions, you can do this. You can do this very easily. So this is the quantity, how many more data you need to sample for your gradients. Okay, so we can have an experiment to show that, okay, if you do this, it's better for Fourier basis solving. For solving low dimensional PDEs using Fourier basis, you do this more sampling, it helps. Yes, so once I have this modified weight of decrease, I can write down all the bounds here. I want to show that the modified decrease is optimal, but it still fails. So in this table, you can see for all the red part is optimal. So for modified decrease, I can just prove that it's optimal for kernel, but it is not optimal for neural network. So why it happens is because for the local random complexity, the localized set, what I choose is actually the ball. You can consider the ball is just my loss function to decide what is the ball. So for the decrease method, the T here will become the H1 norm. So different from the estimating a function. For estimating a function, the TF here is actually L2 norm. But if so this is estimating a function. But for you solving a PDE, the norm here is actually H1 norm. So if you replace the L2 norm to your H1 norm, does this complexity changes? So the answer is yes for Fourier basis, but it's no for the for the deep neural network. So for Fourier basis, why it's better? It's because your H1 norm. It's because your H1 norm constraint will lead to a weighted sum of your Fourier coefficients smaller than 0. If your L2 norm, you will not have this weight. And while you bound your random complexity, this weight actually will help. If you do a Cauchy inequality, you will have this weight here to reduce your complexity. So the difference here is from you can improve the complexity from some D's power to D minus 2's power. So this is very interesting. So you can see this is from D to D minus 2. So if you use D here, you will have some D plus 2s minus 2 over 2s minus 2. And if you go to D from D minus 2, then you will write it down as like D minus 2 plus 2s minus 2 over 2s minus 2. So this is the optimal bound, and this is how this minus 2 comes out. It is from like this weighting, and then you put it into here, and you will get a 2 improvement here. But for a neural network, the local random complexity is always the same. It's because if you want to represent a very oscillating function, as an example, if you want to represent a very oscillating function, you just need a very small amount of your neurons. Like for this function, you just have 4 neurons. You are enough to represent these kind of functions. So this will tell you that, okay, the sparsity of the neural network may not be a very good quantity for the complexity to learning a PDE. We need to find other quantities to do better for the generalization bound, but we still ongoing work. We don't know what's the good complexity. I can't tell you more. And next I will go to stochastic gradient descent. It's a good time to take questions.
Yiping, can you say again how much how many more data you need to sample? You went through that very quickly. I couldn't see the ratio.
It's here. So it's like these times of n. So
I'm trying to plug in that d equals 2s equals 2. So that's 1 over n. So 2 over n. So for 2 dimensions, it's 2 over n. So it's not actually quite a bit of data, right?
Yeah. So for low dimension, so like it's for if D is small. So if D is small and S is small, it's very expensive. I agree. So yes. So I think this is also what we observe, like right for low dimensional problem, deep freeze method is actually not good. But if it goes to some higher dimension, deep freeze method comes better.
Yeah, but not many people solve the Poisson equation in 100 dimensions every day. But
I agree.
In 2D and 3D many times.
I agree. So I think this is one reason maybe we don't need deep freeze method in low dimensions, but just like for quantum applications they needed it. Yeah,
it is an interesting result, a little counterintuitive. I'm glad that pins come on top, but it is a little bit counterintuitive.
Yes. So I think this is because like the pins, like estimating a function, we have a very good theory for estimating a function. We can just plug in all the theory here into pins here, right? So but for the deep freeze method, they have some difference. So maybe you should treat some of the loss function approximation more carefully, but we doesn't know this. This is just the simplest way we can change it into optimal. Maybe it's not the only way.
Okay, thank you.
Yeah, but so that's also the question. So after this paper, I have asked Lexing. So why you select the risk form in your first paper, right? So Lexing tells me, because he thinks if you are using pin to solve a problem, so let's consider the Laplace equation still. So you are solving these equations using this objective function. So you have some term like this, right? You need to minimize this. So if you want to minimize this, you will see a condition number of this matrix. But if you are using the risk form, you just have one Laplacian, right? Because you are minimizing the gradient of gradient of U square. So he thinks that okay, the deep freeze method may have some benefit from optimization, right? So this is what Lexing said. And if you can do experiment, so it is like if I change the L2 loss into higher gradient like the H1 loss and H2 loss, you can see the number of epochs is actually smaller. So you can see the number of epochs is actually smaller. So it's like you are using Sobolev norm as your loss function. The condition number is even better. So it's a kind of very surprising to me. Yes. So then that's the motivation why I do this stochastic gradient descent project. So because Lexing said if you go higher gradient norm to as your loss function, yes, the condition number of this is very crazy. But for the experiments, you can see it's better. Okay, why this happens? So for this problem, I'm also considered the kernel case.
Yiping, I didn't. It's hard to a little too fast. I understand the argument of Lexing, but what are the results that you're showing? Which case are you showing? Are you showing?
So here the case I'm not showing solving a PDE. I'm just for this figure. This figure here is just estimating a function using different losses. But if you are using these different losses, this matrix will still happens, right?
So Lexing is right.
No. So the Lexing is wrong.
Oh, Lexing is wrong. Okay, that's why I didn't understand. So
it's
counterintuitive
so that's
again.
why
Yeah.
I'm saying it's very surprising. Yes.
Okay.
It's like the experiment here doesn't match what Lexing said.
Right. Because that's a
yes, you are using a most relative norm. If you think what Lexing said, you should imagine that if I'm tuning to H1 loss and H2 loss, you should become slower, right? But here you can see in the figure, it's actually faster.
I see. Yeah.
Yes. So why this happens? I want to use a mathematical model to show how this happens. And this figure is actually another kind of interesting thing is that maybe we can just use Sobolev norm. The Sobolev norm loss can accelerate our training, right? So this is another very interesting thing happens for this project. Okay, let's write down what next thing is that let's consider solving this equation. So solving the equation, you can minimize these loss functions. So for the A1 here, the decrease method will select it into one Laplacian, and A2 here is just identity. But for the pin, it is selecting A1 here to Laplacian square, but A1, A2 here. Sorry, I have a typo here. So here should be A2 and here should be A2. So select A2 to be Laplacian and the pin select A1 to be Laplacian square. So this is the difference. And because I want to understand stochastic gradient descent, I can't do it for neural network. I can just do it for kernel regression. So I plug in a kernel regression. I plug in a kernel function here, and I can write down the stochastic gradient descent. It is just a stochastic gradient descent for a projective formulation. I can analyze it very easy. So I will show you some assumptions I give, and I'll show you the result and what it means. Tells you so the assumptions here. The first assumption is called capacity condition for the kernels. It is saying that my kernel matrix, after my kernel matrix, like it is like the population of the kernel features. The population covariance matrix of the kernel features. This matrix is trace of some norm is bounded. What you're saying is that the population covariance matrix of your features have a very fast eigendecay. This is the first condition. And for the second condition, it says that your target function is very smooth. Your target function theta star or the f star is actually a function lies in your Hilbert space, and you do some smoothing on it. So the target function is actually very, very smooth. So this is called source condition in kernel regression. Okay, it is saying that your target function, if you project it into your eigenspaces, it still have another beta-like it still have a beta-like eigendecay. So this is for the target function. If you write it down in eigenspaces, have a beta decay. So there are two assumptions. The first assumption is that the covariance matrix have eigendecay, and another assumption is saying that your target function also have this eigendecay. And the third condition is the regularity condition. The regularity condition is saying that for all the function G is all the function in your kernel space. In all your function in your kernel space, the L infinity norm will be bounded. So why I need these assumptions is because you can imagine I can't get this population covariance matrix. I can just get some empirical version of it. So I still need a concentration bound from this matrix to this matrix. So this condition will give you the concentration from this matrix to this matrix. Okay, so you can see this is very similar to my like a modified version of decrease. Okay, this is for the regularity condition here. So I still have a matrix A1 and A2. I need assumptions on it. So what's the assumption here is like my matrix A1 and A2 also have very fast eigendecay. So for A1, I assume its eigendecay is like P. So like the ice eigenvalue is ice minus P's power, and for the A2 here. And for the A2 here, the eigendecay is Q. So it's like ice minus Q eigen for is the ice eigen of A2. So these are assumptions I have. Okay. So let's see what will happen for these problems if I use stochastic gradient descent to train it. I will have three regimes. The first regime is depend on my mu. So in this regime, it's suboptimal. Okay, so if your beta is not smooth enough, it's suboptimal. And what's the error dominate is like from the empirical covariance matrix to the population covariance matrix, this error will dominate. Okay, and for the second regime is this origin regime. For this origin regime, what it's saying is that you will if you do stochastic gradient descent and with multiple epochs, then the rate will become optimal. And you still have this purple regime. The purple regime is actually beta is very, very large. It is saying that my problem is actually very, very easy. For the very, very easy, what it is saying that, okay, you doesn't even need many epochs. One epoch is enough. You should small your learning rate. You should use smaller learning rate, but not constant learning rate, and a single pass of your data is enough. So this is this purple regime is like you can do online learning because you doesn't need to use the data twice. So you just need to use your data once. So it's like an online learning regime. So you will have these three regimes for stochastic gradient descent for kernel regression. And in our result, we will show that you can still have these three regimes for the PDE problems and what it means. So let's first consider this suboptimal regime. This suboptimal regime is very similar to our deep freeze method. This suboptimal regime, what happens is that the mean error dominated is from this empirical gram matrix to the population gram matrix. So if you want to reduce the error here, you should do some semi-supervised learning by some kernel guys. They have some paper like this. So they're very similar to our deep freeze method. So we want to see how can we also detect this regime for like deep freeze method we are licensing. Okay, this is the first regime I'm interested in is like, okay, the beta here just depend on my mu, and in this regime, you need to do semi-supervised learning because the concentration of this is very slow. This is first second. And for the second question I want to answer is like, okay, another thing I'm interested in is like, I want it to convergence in Sobolev norm, but for kernel regression, they just for L2 norm, right? So we want it also convergence in Sobolev norm. So I also consider the norm I'm convergent have another eigendecay. So I consider is that okay, for the norm I define here, the mu I here is eigenvalues and EI as eigenbasis. So I still have like another eigendecay on your norm to generalize your norm from L2 norm to the Sobolev norm. So if for the L2 norm, it doesn't have like the alpha here. So for the Sobolev norm, it doesn't have the alpha here. It's just like the AI square, but it's Sobolev norm. So I put some eigendecay on your different bases. So I also assume that you should use this norm for convergence. So the gamma here is for the Sobolev norm. So let's see what's our bound here. So for our bound here, it looks like this. Let's imagine what's Q and P. Q and P here, Q is the eigendecay of A2 and P is the eigendecay of A1. So Q minus P here is actually A1 inverse A2, right? So it is the equation. So this is the equation I'm interested in. So you can see the Q minus P here will matches the equations order here. And here, the beta, what's beta? Beta is like how the eigendecay of my target function, right? So it should matches my alpha here, right? So it should matches my alpha here. And for the alpha here is the eigendecay of your kernel matrix. What is dependent is 1/d. So it depends on my dimension. So if you plug in all these things here, you can see the bound I get here will matches the bound of your of the lower bound I introduced in the first section. So in this case, it's still optimal. Okay, and now I will not talk about how I put this bound because I don't have time. But what I will show you is that how many iteration time I need. So what is the SGD time I need for this problem? So if you write down the iteration time, it will look like this. So it looks complicated, but let me explain it to you. So for this rate, you can see the so for this rate, you can see this part is just the same part as what you see is like 2s minus 2t over in the lower bound. The only difference is the part over. So the part over here will depend on alpha is the decay of the covariance matrix, and P is the decay of your matrix A1. So this is the only difference. So you can see here this iteration time have several good things. The first thing is the gamma doesn't happen in this bound. So what it is saying is that if I want my stochastic gradient descent good for different Sobolev norm, the iteration time is the same. So I doesn't need different times model for different norms. This is a very good thing. So maybe it has some applications I'm thinking about is that we can use L2 norm for evaluation so that we doesn't need to take gradient, because this theorem tells me the time is the same for L2 norm H1 norm and H2 norm. So we can use L2 norm just for the evaluation or for early stop for selecting the early stopping, right? So because the time here doesn't depend on gamma. And for the second equation of this bound is like if my beta is large. So if my beta is large, my beta only appears here, right? So my beta only appears here. So if my beta is large, you can see this one will become very small, and the piece, in fact, over all the function will become very small. So yeah, like if my function is very smooth, I doesn't need to consider what kind of problem I'm considering. It's only like for hard problems I need to consider this. So this is two implications first from this bound. And from this bound, the main question I want to answer is the decrease method versus the P. How can I compare them? So how can I compare them? It happens for I have different A1s, so I have different P's. So here I can tell you the story why I have Soviet F norm, it can converge faster. So the reason is here. So the reason is here. So if I want to compare DRM with P, I need to consider the impact of P over this bound. But for the problem, you see I write it down as alpha plus P. But for the problem I'm considering, like the kernel with P for PDE, for the kernel matrix, the alpha is larger than 0, and for the PDE, the P is smaller than 0. Why? So for the kernel, the covariance matrix is always an integral operator, but the PDE here is a differential operator. So you can imagine these two operators, they will have very different behaviors. For kernel smoothing operators, the higher frequency will have smaller eigenvalues. They will smooth it. But for the PDEs, for the differential operators, if you have for the high frequency part, you will actually let it become larger, right? The eigenvalue 0 will become larger. So the differential operator looks like it helps to balance the condition number of the kernel operator. So the kernel operators, it have a very large conditional number, right? And my PDE operator will help you to cancel the effect here. So that's why the ping will become faster in our bound. Or you are using Soviet norm, will become faster. It's because if you have more gradients here, I can cancel more for the kernel operators. Unless your alpha minus P, well, you should keep it always larger than 0. You should keep it larger than 0. Yeah. So you should have this term, and you should let it larger than 0. So the P selection will depend on the smoothness of your kernel. If you are in a neural tension kernel space, you should consider that the P will depend on your smoothness of your activation function. Okay, so this is what this bound tells me, is that if you are using a Soviet norm, you can actually accelerate training. So because the Soviet norm, the gradients is actually can cancel in the smooth operator of the kernel. So this is what it's saying. So because the time achieved, so I just summarize the talk. So it is like we introduce a nonparametric statistics view of numerical PDEs. So when you design your loss functions, you should this viewpoint gives you some new constraint to design your objective function to let it to become statistical optimal. And for the first part of the talk, it is saying that the sparsity of the weight is not a good measurement of the complexity of your gradients. So you need to consider other norms. And maybe for the algorithms, we can design some regularization, but still it's ongoing work. I can't say anything about it. But for the second part, it is our ongoing paper, and we will hopefully publish it at the beginning of the next year. So it is a stochastic gradient analysis suggests that if you use a Soviet norm to train it, it can actually accelerate your convergence. So it's not just like P. You can add a Soviet norm to P. It can help your training. It's because the differential operators can help you to cancel the condition number of a kernel matrix. So I think this is the take-home message of this talk. And for the first part of the talk, the paper is here published, and for the second part of the talk, the paper is still ongoing. Yeah, and thank you. And for if you have time, you can have questions.
Thank you, Ziping.
Yeah.
Do we have questions?
Thank you very much, Yiping. That was really excellent. I had no idea actually that I mean the both. You have two surprises today for me.
Yeah.
Both the first part and the second part, but on the stochastic gradient, are you implying that let's say for just function regression, I should use the Sobolev norm so that I can, because stochastic gradient descent would be more favorable for that?
Oh yeah, so it's not like for function regression, it's also for solving PDEs, because I have A1 and A2. You can like A1 and A2.
Yeah, for solving PDEs, you make the point.
Also for training, yes, for regression, it's true. I'm still running experiment because I want to catch up this talk. So I'm writing proofs these days to get these rates. So I'm still running experiments. So I want to show that for training, Sobolev norms can help, but here is a drawback. So if you're using a neural network, if you want a Sobolev norm, you need to take gradients of your neural network. This part is somehow expensive for estimating a function. Yes, so this is the drawback for each epoch. It will become longer, but maybe you can converge faster. But for kernel matrix, it doesn't have any problems. For kernel matrix, if you want to take gradients, you just need your kernel matrix to take a gradient. So this one is very, very, very cheap. So I'm making experiments on kernels. So it's just for kernel regression. You can say that Sobolev norm it can be faster. Yes.
That's good.
Yeah.
I don't know if John, you have any questions?
No, I don't have a question.
Are you surprised?
Yeah, lots of things to catching up. So yeah, good talk.
So if we have no more questions, we could move to the second speaker. Thank you, Ziping.
Thank you, Yiping.
Yeah. Thank you.
Tricia.
Our second speaker today is João M. Pereira. He would be presenting on learning laws of datasets. So a little bit about him. João is a postdoc at Odin Institute at UT Austin, working with Joe Kylan and Rachel Ward. Previously, he was a postdoc at Duke University working with Wahid Tarok and obtained his PhD degree in applied mathematics at Princeton University, advised by Amit Singher and Emmanuel Abbé. He is broadly interested in machine learning, tensor decomposition, and information theory, and he is here today to talk about his work in the learning laws of datasets. With this, I leave the floor to you. Thank you.
Let me share my screen. So can anyone see the slide?
Yes, we can see your screen. Yes.
Awesome. Okay, thank you for the invitation to talking about this. Today I'll be talking about learning laws of datasets. So it's a little bit different than Yiping. The idea here is that you don't know the PDE or you don't know the equation, and you actually want to figure it out using machine learning. And so, so the idea is that normally to get these laws, for instance, the law that Yiping focused on some of these laws, like the Schrödinger equation or the Maxwell equations, as I have here. Can you see my mouse? Can you see my mouse or
yes,
not?
Yes, we can.
Okay, awesome. So here you have the Maxwell equations, and we have an electromagnetic field here, which is governed by electromagnetic equations. Here I put a plot of a Brownian motion, a simulated Brownian motion, and here I put an image of some retina, image of the retina. The idea here is that this is governed by a PDE that we know. We got data, we performed experiments, we had a lot of data, and we had to feed a model to this data. And with this model, we figured out that the best possible explanation was the Maxwell laws that describe this. The stochastic differential equations was more or less the same thing. We started seeing that the increments were independently distributed and followed some Gaussian distribution. And so the question is, if we are now given a data that we don't really have a model for it, like this image here of a retina, can we figure out like what's the equations that govern this, or even the variables that govern this? And this was the goal of this project. So, and this was a project with more than one work, and the idea was to create an AI to assist in learning equations. The idea of the AI actually would be like a more meta thing, something to do in the future would be something that would actually perform the experiments, get the data, do everything by themselves. In the beginning, you have to figure out something that once you have the data, gets you the equations. And so this was the project. And we have two models on this. And first, what are these laws of nature? How these are described? Most of these are described by equations that govern evolution, and this evolution normally is described in mathematics by differential equations or difference equations, basically things that we are going to tell you how the system is going to evolve. And main equations that are mainly considered are the ordinary differential equations, partial differential equations, and stochastic differential equations. And so this talk is going to talk on, I'm going to talk about two methods that we developed during the year. So this is a work in collaboration while I was in Duke, and I'm still working on with them. And we developed first a method for learning PDEs, and it also works for ODEs. By the way, I don't mention it but ODEs can be thought as a particular case of PDEs. And then secondly, I'm going to talk about the method for learning latent SDEs, and I'll explain what these latent SDEs afterwards. So here, the idea is, and I imagine a lot of people here watching this talk know what a PDE is. I'm also going to present some examples afterwards. But so the idea is that we have noisy data points of a function that is governed by a PDE. So here I put just the example of an ODE, and actually one of the simplest ones, which is the exponential function. The exponential function is the solution to this ODE over here. This ODE is the derivative of the function in time is equal to the function itself. And the solution is exponential. And now suppose you have samples, which is like the exponential function plus some Gaussian noise. And now you try to fit a neural network to it and also learn the PDE at the same time, or in this case, the ordinary differential equation. So you first basically want to learn that fit a function to it and then get the derivatives out of it. And so our idea to do this was, so the main idea is to use the universal approximation theorem. And so the universal approximation theorem guarantees you that if neural networks, you have enough, you have a big enough architecture, and there's different versions of the theorem, but the bottom line is that if you have a big enough architecture, you can approximate functions arbitrarily well. And not only it's the functions itself in L2 norm, but you can, so for people that are familiar, you can approximate it in Sobolev norm. For people that are not familiar, Sobolev norm means that you can approximate it both in L2 norm, but also L2 norm of the derivative. So even the derivatives are close to the original function. And so what this means is that because you can approximate also the derivatives, it means that the function, this neural network that you're approximating the function, that is approximating the function you're looking for, also is approximate solution to the PDE. And this can be shown, it works for any kind of PDEs, and in particular, Karnadakis has work that he shows this for parabolic PDEs. I think that's the only case, but it actually works for any kind of PDE. And correct me if I'm wrong, and then, so the idea is to train the network to approximate the data. And then once the network is approximating the data, hopefully it will also approximately solve the PDE. And we can use the auto differentiation to calculate derivatives of the function and then try to relate them to get the PDE, the underlying PDE. And how we're going to use the derivatives and relate these derivatives to get the PDE. So most PDEs are normally a linear combination of simpler derivative terms. So you can take, so one example is the wave equation, where that governs the evolution of a 1D governs the evolution of a function that is actually more or less two waves going in different directions, and it's governed by this this partial differential equation. Here only has two terms. The second derivative in time of the function is equal to the second derivative in space of the function. And then the heat equation that governs the dissipation of heat in the over time also is it has two terms. Derivative in time is equal to the second derivative in space. The same thing for Helmholtz equation and all these equations that I put here. Normally, all known differential equations can be written in the linear combination of few terms. Also, something that happens is that sometimes physicists and biologists have kind of an idea of which terms should appear in the PDE. And so what we're going to do is we're going to build so before we start training, we come up with a dictionary of possible derivative terms we want to see in the PDE. We think these terms should appear in the PDE. And now the good thing about these terms is that they don't need to be all linear. Like you can have, so you can have products of functions. So u times ux. So this PDE doesn't need to be linear. And so you consider a linear combination, you put them as many dictionary terms as you want. And now you're looking for a PDE. So here I put 5 terms as an example. So u, the function itself, u, the second derivative of u in terms of x, and then this product here, and the third derivative and in time. You can put whatever you want in terms of like you can put functions that depend on x. You can put other products of u. It's just a dictionary of functions that depend on u. And now you're looking for the coefficients a1, a2, a3, and 4, a5 that solve these equations. So an example of an equation that actually can be written like this is the heat equation, where a2 would be 1 and a5 would be -1, and you get the heat equation. With you also have some coefficients that give you the Inverse-Burger's equation. The same thing for the KdV equation. And if you wanted more equations, you could put more derivative terms and to build a dictionary. So is there any questions so far? Okay, I'll continue. Okay, so how to recover this PDE? So if you sample random points in this domain, on the domain that the PDEs live on, so you assume they come from some samples. These PDEs live in some domain. So if you sample random points in this domain, then and U is a solution to the PDE, then if you evaluate U and all these derivatives of U at these points, this is going to be equal 0. And to evaluate these derivatives, you can use auto differentiation, as I said before. And so you can evaluate this for a neural network. And so you evaluate these in a bunch of points. For P1, P1, Pk, you evaluate these in a term of points. And you build this matrix here. So for the number of columns is the number of dictionary terms. The number of rows is the number of points you sampled in the domain. And then you can always, like in each epoch, you sample random points at random points in the domain. And
oh, I have a question. Yes, by doing that, you commit to the boring integer calculus. I like fractional calculus. How would you deal with that?
Oh, you need to do fractional derivatives of U, maybe some kind of parameterization of U where fractional derivatives are easier to calculate. But in
one of our papers, we show that you can, let's say the advection diffusion reaction or the advection diffusion equation, you can write it actually as a 2-term equation because you have a fractional derivative. So, but if you commit to this, which is a standard thing that people do, you get back to the old way of doing things. You're not going to discover anything other than the equations that are already known.
But okay. Oh, so you're saying like you want also to recover the exponent, the fractional exponent.
Yeah, exactly. The operator. Yeah, kind of.
Exactly, which now you can do it like, yeah, we can't do that right now. Like maybe you can, like you can put it maybe as a parameter.
Yeah.
And take this fractional derivative. And I think maybe if you put it as a parameter, it should work. Because it was it worked very well already for, so maybe if you put one of these dictionary terms with the parameter also that is this fractional exponent.
Yeah.
And with this matrix form, then you might be able to do that as well. It's a good idea to pursue. I don't know much about fractional derivatives. I would have to learn, but we should discuss this maybe more offline to know if we can actually implement this. But I believe if it's something that you can calculate for a neural network for any exponent, then it should be doable.
But it would have to be for a fixed fractional power, right? You could add a bunch of columns that were like, for like the computer, like alpha is like a quarter, a half, 3/4. You could add those in as columns. Do I understand correctly? That this is not like a train, these are not trainable, these aren't parameterized operators. These are just.
Yeah, but like imagine you could parameterize them. There's nothing in this paper that doesn't say these u of x's, these derivatives can't be fractional. And so it's something we haven't done because normally the derivatives are integers, right? But I think we can put the fractional exponent in these columns.
That's my question. Can you have parameterized differential operators in your dictionary in this approach? That's my question. Yeah,
I think so. If you can take derivatives of these exponents and yeah, I think so. I would have to look for it because it's something I'm not very familiar with. But if you can take alpha as a parameter that you can now optimize, sure, because this is all going to be calculated with a neural network loss anyways. So I'll explain later and maybe you can see better, but I think so. I hope so.
Can I comment on here, this slide?
Yes.
This is João from Brown. The solution for this equation is 0. Then exactly. It will give you 0. So I don't think, I might miss something, but yeah, I can tell that the solution is 0.
Exactly. I know. So I'm going to explain what we're going to do. But that okay. To explain that. So that's something. So the idea is that okay, so there's nothing. So I'm going to call this matrix here, this operator M, operating on U, and then evaluate it on this boldface P, because boldface P is a bunch of points. And then, and so what, sorry, I didn't catch your name. Or, so what the previous, what the person that just spiked last just pointed out is that A is in the null space of this matrix. So it can be 0, but the point is that A is in, so this matrix must, for this to have a PDE, be a solution to a PDE, this solution must be low rank, and A must be in the null space of this matrix. And so now what we're going to learn is the null space of a matrix. And so the null space of so in practice, calculating null space of a matrix is done by SVD, or at least that's the way I normally do whenever I have to figure out the null space of a matrix. The reason it's done is SVD is because matrices in machine precision, most of them don't have a null space. They have a very, like there's the smallest singular value, it's always a little, it's different than 0, but it's very, or it's practically what you'd call a null space. And so you go by calculating the smallest singular value that is 0. And so, but in our program, so we could just put SVD on the problem itself, and because SVD has gradients and also, but we're going to add some things also to A. So we're going to use the min-max principle to get the smallest singular value. And the idea is that if you minimize this program, if you solve this program with mu and p fixed, so think of a matrix, and then you're just minimizing over A, this is going to give you the smallest singular vector. This is called the min-max principle for singular vectors. There's also the same thing for singular values. And an important point here, which was already more or less mentioned, is that you have to enforce the norm of A to be 1 at every step. Because otherwise, if you don't, the minimum of this is going to be 0. And the minimum is going to be A equals 0. So at each point in the gradient, what you have to do is you project the gradient into the, let's call it the projected gradient in sphere that only goes in the tangent space. And even then, after you do the optimization step, you have to project. So you always have A to be norm 1. So, but once you have this, so now that—
Sorry, can I ask a question about that? Can you go back a
yes.
slide? So why can you add that constraint? I understand that you want a non-zero constraint to avoid the trivial solution that João mentioned, but what if the like say you have a PDE that's like a quarter u plus a quarter u partial x of u, right? In that case, you have it's a quarter plus a quarter.
Yes.
Right, like why? Do you see what I mean? Like that's not tied. PDE might not satisfy this constraint.
So if the PDE, if you only like so if A is a solution, if the PDE is solved by, sorry, let me explain. So if this is if the U is a solution to this PDE, then A is in the null space of this matrix, which means that this solution of this problem is actually the PDE itself, right? So the reason I'm adding this L2 norm is because this problem here that I'm circling, this is actually the min-max principle that gives you the smallest singular vector. That's going to give what we're looking for. So it's not smallest singular vector, it's a singular vector with smallest singular value.
Right, I followed that, but the question is about A, right? A is the vector of linear it's the coefficients of your dictionary, right?
Yes. I want it to be the smallest singular vector, and this is—
I understood, but the problem is that those coefficients might not sum up to something with norm 1.
Oh, that's a good question. So if you have this function here, you can always scale these out, right? You multiply by a scalar on all of the AIs and still get the same thing to be 0. So you can always have the same answer up to a scalar.
Okay, perfect. Thank you.
Right. So if I arrive here, okay, so you understood. So you
got it. Thank you.
It to be norm 1. And so the idea is now that you have you have three things here. So we have 2 things right now that I've talked about. The first one is try to fit the neural network to the data. And so let's say here that you have sample points. So pi is the location, UI is the function value. You want to minimize the L2 loss. You might also want to minimize other kind of loss if you know anything about the noise. But let's assume it's Gaussian noise, so you'll want to minimize the L2 loss. So you minimize the L2 loss of the between the neural network.
Can I quickly ask one follow-up question in your previous slide?
Yes.
You know that this looks like constrained problem can be done by unconstrained one by reducing the one dimensionality. Then you can solve it exactly by solving just the
what do you mean exactly? Like no, this has an exact solution with a small singular vector which you can calculate is
Right. So, so your goal is to solve this minimization problem?
yes, but this is going to be part of the loss.
Okay, so this is not your end up goal.
This is only part of the loss. Yeah.
Okay, got it.
Let me try to go over the loss first, and then ask some question afterwards. Or maybe it will be better after I answer this question. But the point here is that there's two components I've talked before. The first one is to try to fit the neural network to the data, and the second one is try to determine to learn the neural network. And for this, you minimize over A. So you also minimize this loss. So this is the first part, you want to minimize this. This second part, you want to minimize this. And then we also add the loss parsetting concern. So we add the L1 loss to A. This is going to encourage A to be sparse. Why is this? Because as we saw before, most laws, most PDEs are actually a sum of a few components. And so you put it a dictionary of a lot of them, but you expect only some of them to appear. And so you put this L1 constraint to make sure that only the most important components are coming up, and you get really a PDE that's what you're looking for. And so is there any questions right now about, now that I explained the three losses? And let me just say, so this is how you optimize it. So this is how we joined. We tried a bunch of different combinations of the losses, and this seemed to be the one that worked better. And so an important point is that we have to enforce at all times that the norm of A is 1. Otherwise, things might go out of, might get a problem.
Can I ask a question here? So, so this is interesting, the idea of the SVD piece, but this is similar to Cindy. Are you familiar with Nathan Kutz's work?
Not sure, but is this the paper? There's a paper that does this, but the time is fixed, so there always needs to be time there. And is that it might be that. So is that for equations?
Yeah, I can share the reference in the chat so that you have it. But what they're doing is they do dictionary-based learning with the L1 regularizer, and they're trying to fit, the right-hand side of an ODE or a PDE or whatever.
Oh, I see. Yeah, it might be.
It
might be
that
that
is the way you've set up this other part,
yeah,
the SVD.
So so this is an addition that I think it's important. So for that model to work, you need to have one term that is going to show up. In that case, the derivative in time of the function, and then you have other terms that you're learning. Here, it doesn't need, you don't think, so you don't assume any of the terms is going to appear. And in particular, you don't give any importance, like all the terms have the same importance. So you really are blind. You have no idea which term should appear, which term should not. So this is good for that case. So cases where, for instance, most of the times you have things that evolve with time, and then you have some space. There you should, you expect the derivative in time to appear. But sometimes it's just space. You have some model of the space, or sometimes you don't even have any idea of what kind of variables or their combination. And so for those cases, you have this model that doesn't put any more importance on any term of the derivatives.
Yeah, so they have all of those same pieces. It works the same. It's just a different algorithm for how to train that dictionary. They have some issues with, they try to promote sparsity in the same way, but they have to do pruning in order to get it to work. There's a lot of details and like pathologies that they run into. I just want to suggest, since you're training it differently, it might be nice for you to do an explicit comparison and see if you have an advantage in terms of this SVD versus, because their approach is at this point very mainstream. not in this crowd, I don't know if it's okay to say, but it's like maybe as mainstream as pins in terms as of a very widely used thing. So if you can fix that, you know, that might be a big
Sounds
impact.
good. Yeah, I'll take a look. Cindy, right?
So yeah, I'll put the paper in the chat.
Awesome. Okay, thank you. Yes, and one last thing before I show the results is that we had an unintended consequence of this is kind of great, is that when we minimize this PDE, so this when we think of this minimizing this PDE in terms of theta, so theta is the parameters of the neural networks. So when we think of this term in terms of theta, this is asking the neural network to actually solve the PDE that it has learned. So it starts by trying to fit the PDE at the beginning. At some point, it also starts to try to learn try to fit the neural network, try to regularize it to be a solution to the PDE it has already learned. And this has the consequence of being able to smooth the function a lot. Instead of trying to over parameterize, it's just going to try to be a solution to the function, try to regularize the function to be a solution to the PDE that's just learned. And the consequence is that the function that is learned is much smoother than it would be if we just did these things separately. And so these are the results. I'm going to put here some example of the Helmholtz equation. The equation is given by this. So we have two dimensions, x and y, and the equation is second derivative in x plus second derivative in y plus the function itself is equal to 0. And this is one of the solutions of the Helmholtz equation. There's several solutions of this equation. And here we consider a dictionary, a derivative dictionary with 8 terms. So second derivative in space, second derivative in x, second derivative in y, all these that you can see. I also put here the coefficients we're looking for. So A should be a multiple of 1, 1, 0, 0, 1, 0, 0. So a sparse vector that should give you this. And so this is the solution of our algorithm. So as you can see, it's practically equal to the original solution, although the middle and the samples were like the samples that the neural network got were very, very noisy. It still was able to get a very similar approximation to the original one. And we also was able to recover the original STE. So this vector 1, 1, 0, 1 up to an error. We defined the error in the paper, which is 3.6 to the power of 10 to the minus 2. So the idea is that we get 2 digits out of the law, which is not bad given the number of samples and the noise. And so is there any questions so far about the method?
What's the level of the noise? It looks big. What's the level of the noise here?
It's, I think the SNR is 1 or something like that.
Sorry?
SNR is 1. So the noise it should be around a Gaussian at each point. So like, so the function value of this thing is between -3 and 3. So it should be the variance of the noise. It's a Gaussian noise with variance, I think 1, 2, or 3, maybe 1, I think.
Okay, that's pretty big, yeah.
Yeah, so this is, and something I didn't include it, but it for small, for big noise, this method was really good. When the noise was really small and you'd expect the law to be learned very much better, we got into problems, I think, because we couldn't get an architecture that would fit the thing well enough, because it really needed to be good to compare to the errors we were expecting. Also, so we compared this with the Cramer-Rao bound, which is, so we obtained the Cramer-Rao bound for this, something I know how to do in some problems. In particular, we got a Cramer-Rao bound, which gives you an idea of what's the best anyone can do. And and we actually got something very close. But then when the noise was very, very big, when the noise was very, very small, we'd be farther away from the parameter bound. So that's what was one point that we'd like to improve. And so that's it. Any more questions?
Yes, specifically when there is no noise, what kind of coefficient error can you get down to?
I don't recall right now, but 10 to the -4, 10 to the -5.
Like the same sort of error that you would have in the reconstruction with the neural network, is that the?
Exactly. And
Yeah.
yeah, and the problem would mostly be architecture not being big enough. And then if it starts big too big, it also takes more time to train. Or I had some ideas of how to fix this and ended up not doing it yet, but maybe if we do some kind of polynomial kernel or something is kind of smooth and can approximate things fairly well, maybe it can be get quite low. Also, it might be at some point, if it starts to be too low, then the gradients and numerical precision is going to play it's going to have some effect on that that's going to make it harder. So, but it's a good point to try to figure out what happens if the noise is very, very small. But
is it actually sparse what you're picking up? Like how close to zero are the zero entries that you're learning?
It's so that's a good question. Most of the bad things were on the entries that were not close to zero enough. So it might be also that the way the gradient because the gradient close to this zero, this L1 is not smooth, right? And maybe that's causing also some problems for at least for learning A. We also have some ideas to modify this, not to to be a more maybe don't optimize over A or optimize it in some better way that actually gives a more optimized solution. Because so if there's no sparse solution, you actually know what is the minimum over A. So maybe you can optimize that minimum and then you take derivatives considering that. So I don't know if this made a lot of sense, but there's some other ideas we're thinking of trying to make sure the sparse vector is really sparse. And it's not clear that we're actually getting something that maybe it should be more sparse than it is.
Please proceed. We asked a lot of questions already.
Yeah, and I'll probably try to speed up a little bit on the second part. And okay, yeah. So the second part is about learning STEs, and in particular latent STEs. I think this is a very cool project because it takes images as an input and tries to get stochastic differential equations. So an example is the following that I have on the left. Imagine you have a yellow ball, so it can be anything, but let's imagine you have a yellow ball moving around with moving around in the XY space, and the coordinates of the ball are governed by a stochastic differential equation. And what you want to figure out is what are the parameters of this stochastic differential equation, and what are the actual latent variables. So this is a very ill-posed inverse problem because you have no idea what is the actual latent space, and like you can do all kinds of transformations and still get a stochastic differential equation. But maybe we can do something smart and get some kind of class that's stochastic differential equations that we care about. So I'll talk about that. So let me first give you a crash course on stochastic differential equations for the people that are less familiar. So, and the only thing I'm going to tell about stochastic differential equations that I think it's important is that they have two terms: a drift coefficient, which is the deterministic term, and the diffusion coefficient, which is stochastic. So all the SDs are some kind of, can be thought of as ordinary differential equations where we put some randomness into it. And the randomness is defined by this diffusion coefficient. If the diffusion coefficient, for instance, was 0, then the drift, then this would be ODE. And now, or to define, now that we know a little bit more about these SDEs, our model is like this. So we have some input X. So we only know about X. We don't know anything more. And we want to recover both F. So we want to recover F and then mu and sigma. So these are the three things we want to recover. We don't know anything about F. We don't know anything about mu. We don't know anything about sigma. And so another thing, oh, sorry, I'm muting myself. Another thing I'm going to say about SDEs is that if you have SDEs have this transformation that you can do, that if you have an SDE and you apply a function, and let's assume for now that G is 1-to-1, it doesn't matter for Ito's lemma, but it will matter later. If you apply a 1-to-1 function to this latent space, you still have an SDE. It has different parameters, so this tilde mu until the sigma are different than mu and sigma in general. The formula for them, you can actually get a formula for tilde mu and tilde sigma in terms of mu and sigma and G. So Ito's lemma actually is about that, getting formulas for tilde mu and tilde sigma in terms of mu and sigma. And so if you apply any 1-to-1 function to the latent space, you still get another SDE. And so there's this equivalence relation. You can never, so if you only know XT, right? Who's to say that you see F, mu, and sigma, or you see F tilde, mu tilde, and sigma tilde, where this YT is just a function of G, and then this mu tilde and sigma tilde depend on mu, sigma, and G through this Ito's lemma, and then F tilde is equal to F is equal to F tilde after G. So if you think about it, all these give exactly the same samples. So there's no way to distinguish between F, mu, and sigma, and F tilde, mu tilde, and sigma tilde. Does this make sense? So this idea of latent space, you can't distinguish between this.
Yes, great. Please proceed.
And so the idea is that we have this 1-to-1 transformation in latent space, and we're going to restrict the number of parameters we're looking for, and we're going to do this in a way. So if F, mu, and sigma have some technical conditions, in particular the conditions on sigma are a little bit restrictive, but are the ones that a lot of people consider in practice. If they have these technical conditions, then you can transform your latent space so that the sigma is isotropic. So everywhere the diffusion coefficient is the identity, without any scalar at all. So basically what you get is that you don't need to learn the diffusion coefficient because you know what it's going to be. So because you don't know anything about sigma, you might as well consider it's the diffusion coefficient. And more or less, that's the idea. And now we're going to focus on learning the rest of the parameters, in particular F and mu. And so to do that, we consider a variational autoencoder, and we factorize it in this way. So think of X, bold F, X. So you take the samples you get, and you think of them as consecutive samples, and you pull every two consecutive samples, and you make that into bold FX, and that's your latent variable. That's your observed variable. And your latent variable is this bold FZ, which corresponds to those those variables in latent space. And now you consider this expansion where so xt is equal to ftz plus some noise, and then zt plus delta minus zt. So the prior z decomposes in some part that is only for zt, and then zt plus delta depends on zt is governed by a SDE. And then xt and xt plus delta are related through this function f. And so if you write it in this way, then you can write the actual loss in this way. So I use here the Euler-Mariano approximation for stochastic differential equations, which is something like if the delta t is kind of small, the increments are approximately Gaussian. And if you use that, and assume the delta t's are approximately small, you can try to learn this using a Gaussian, considering a Gaussian increments. And this is the formula you get. And then for PF, you get, so the error is kind of a Gaussian. You can think of epsilon as a Gaussian, but you can define it as wherever you want it to be for learning the thing. And then gamma can be any prior you want for ZT. No, we didn't even put any prior at all for, so think of it as uniform or something. And then the decoder, you decompose it in some way. I'm not going to go much over that. And then the loss is a typical VAE loss, but thinking of this bold F and X and bold FZ as the latent variables. And so this has two parts. One is the blue part ensures that the posterior approximates the untractable P phi z of X. And the other thing is maximizing likelihood of P phi of X. But that's not actually how we calculate. We can calculate it using this thing on the bottom and plus a few tricks, because all these terms can be actually calculated. Like using reparameterization tricks, and there's 3 tricks. It's better to check the paper for details. I think it's better to talk about that in the paper if you're interested, or offline. And so how much time do I have left? I have 7 minutes. So
take your time to finish this, because this is really interesting part.
Okay, so we have also an identifiability theorem, and I'm taking here some of the theorems and putting them together and not mentioning some of the technical conditions. But an interesting part of this, and one of the main theoretical results on this paper that I think is very interesting, is that if we have a generative model like the one we considered before with the VAE, then under some technical conditions and in the limit of infinite data, as that data keeps coming, the VAE we propose is going to learn the actual 2 parameters up to the orthogonal transformation or isometry. And this isometry, you can't get away from it. Since we don't know anything about the latent space, whenever you have an SDE with the isotropic coefficient, if you apply it an isometry, you still get an SDE with the isotropic diffusion coefficient. So if you multiply your samples by orthogonal matrix, or if you add them a vector, that's not going to change the isotropic coefficient. It's not going to change the diffusion coefficient. And so the best you can hope for is to get the result up to this isometry, and we guarantee that. And this is a result that, so we borrowed some ideas from a recent result on that considers independent componental analysis with VAEs. And we use some of their ideas to prove this. And the idea is that if you have some semi-supervised, if the latent is somehow semi-supervised, the latent space, you can recover you have this identifiability result here, or semi-supervised variable is the next iteration is supervised by the previous, like the previous latent variable supervises the next one, or something like that. And it's a decomposition that the ideas are similar, but the proof is and the proof is similar. The ideas sometimes can be a little bit different, but the interesting part is that we do have an identifiability result. And I'm going to show here some results. Instead of just So I'm going to focus a little bit on the reconstructions because I think this was a really good job. So think about these images, right? So the reconstruction looks really good. And think about, so this is a STE with 2 dimensions. So the latent space has dimension 2, and it's still got very good reconstruction. And this method works for, we've seen it working for a lot of different stochastic differential equations. This was the first problem we considered, a ball moving in some square, but we also consider a different problem. Imagine you have 2 images, and then you do a Wasserstein interpolation between them. So when you do this Wasserstein interpolation is controlled by a weight, right? Can be 0 and 1. 0 is one of the images, 1 is the other, and then any point in between is some interpolation between the 2 images using the Wasserstein barycenters. And so this can be computed offline. And now our idea was, so let's do something that takes this coefficient that gives you the interpolation, now is moving with an STE. Now it's moving with a Brownian motion. And now you have this Brownian motion that controls the movement of this coefficient. And for each coefficient, you get an image, which is the interpolation of the 2 images. Can you learn the underlying STE? And the answer is yes. It also worked for that particular model. It worked if we added a lot more balls. If we added, and this I think is also an interesting result because it has this ball, which is movement in X and Y space. It also has the iteration of the background using this Wasserstein interpolation. It also worked for that case. We also added noise, and it didn't seem to bother the method much. I mean, you see the reconstruction is a little bit more affected, but otherwise it still worked in learning the stochastic differential equation. And we also have, we also analyze a real data set, which is, so it's images of an atom moving in some space. And we fit our model to try to learn the Brownian motion of the atom. And even so, something interesting happened which is that when we put to be 2-dimensional STE, it learned the position of the atom. When we put it to be 4-dimensional, 6-dimensional, it started also to learn the deformations of the atom and the rotations and things like that. So it was starting to learn more behavior of the.
I have a question, João. When let's say that you have the blue balls, right? Can these balls interact? For example, could be molecules and governed by some potential, attractive potential or repulsive potential and so on. Can you have interacting particles? Is that
yes, I think so, because that's still an
sure?
STE, right?
Well,
yes,
it is, but okay.
I hope so. But I would think it would be better to try to figure out a parametric version for mu in that case, so that the neural network is not, because the neural network is also trying to learn the diffusion coefficient. Maybe it's better to just have a kind of an idea of a parametric version of mu or some smarter way to learn mu, so the neural network is not stuck trying to learn things that are not there. But otherwise, yes, you can. I think you can learn things with potential and potentially learn what is the potential, which I think it's also something that would be interesting. And are there any more questions?
No, it's good.
Hi.
Sorry.
Hi, Joe. Can I ask a quick question?
Yes, Chan. Yeah, yes. I asked a question for you. That's because you didn't ask it.
Okay. So just a quick question, like regarding this figure, like is it like on the training data set, or like is it prediction? Because like I'm a little bit lost, because like you cannot predict like a specific differential equation in some sense, right? Like there is always stochasticity. Like I'm wondering like what you are plotting in these figures if I missed some?
So this is the, okay, so this is the map to latent and then back. So this is a VAE, right? You encode the image and then you decode it.
So this is the autoencoder part, right?
Yes. So, but
Okay.
the encoder also gives you the drift and everything. But yes, this is the, so the auto, as I explained before, so the autoencoder has a bunch of components. Here, I didn't go much over it in detail, but it has it learns F, which is the encoder part, and then the Q, which I didn't talk a lot about, it is the decoder part, which learns the encoder. So it has the F, which is the encoder. It has the other part, and it also has this mu. It also learns the drift coefficient, the VAE. It's everything in one. And
Yeah.
showing just what happens if you encode and then decode. But it's also learning different drift coefficients, and we have error estimates. But I didn't want to put it here because it's just be a table of numbers that, if you're interested, you can check the paper. It's doing a good job. It's still working better in more noisier regimes that more stable ones. Still doing a good job, at least compared. You also got Kramer-Rao bounds, which give you an idea of how good you can do. Kramer-Rao bounds are kind of crude. They're just the same idea, but you still got something that was at least scaling as much as the Kramer-Rao bound, which was awful. So I think it's doing a good job.
Oh, and also like I'm curious about like the latent dimension that you choose. Is it always 2, or like it can also be like a larger number? Like yeah.
Oh, so that's a good question. It's we have to figure out how to choose it. For most of these experiments, we just knew what it was and we put it like that. In practice, you should figure out. You should try to figure out what you use it. So one thing you can do is just try different dimensions and see what you're getting. And in particular, like at some point you'll get something that will be happy with. Like you can like do a plot of what you're getting versus the number of dimensions, and at some point you'll get something that you'll be happy with. Does this make sense? But we also have, so, and I was going to just mention some of this. We have some additional considerations we do in the paper, like, because this is it can be adapted to different applications, and that was our aim. And we put some practical considerations that people might think about when implementing these things. You can have a sampling frequency that it doesn't need to be always the same time. Although if you have longer times where the sampling frequency is very big and then the Euler-Mariam approximation is not good, you should have some kind of different integrator. We talk a little bit about that in the paper. We can also have SDEs with time dependency. And what you're asking now, which is the question about determining the latent dimension, we have some ideas for that. An idea that I think it's more like robust to these things that we're looking for. It worked more or less, like it was not the best thing, but it worked fairly well, is this idea of like looking for the eigenvalues of so instead of having an isotropic diffusion coefficient, you make it to have a diagonal with learnable parameters. And now you're trying to make this diagonal to be sparse. And so you put L1 error, L1 penalization in the terms of this diagonal, and this is going to ask for this sigma to be sparse and try and gives you more. The sparse pattern is going to give you the latent dimension. So that was some of the ideas we tried. I think are the most useful. There's something also with the Ike criterion that we consider, and so those are the main two ideas. We have a paragraph on these ideas. We also have some Kramer-Rao lower bounds for estimating this error to compare what we're doing with what any estimator would do, or what would best estimators do? And that's it. Is there any questions so far? If there's no question, let me just say, so my collaborators were Ali and Sina and Vaid in Duke. We worked together on this project, and these were the main collaborators. And at some point, Robert, okay, let me, sorry. Okay, I think I did something.
You can try sharing.
Okay. I see. I did something wrong. Let me. Okay. So I wanted just to say that Ali was the one that coded everything. So a big shout out for Ali for training all these models. And these are the papers that you have to see. And the code is all available on Ali's GitHub. And these are the links. And if you go to my GitHub, you can also see the links for these repositories. And that's it.
There's a question from Oskoi. I guess he has raised his hand.
Yes, can I ask a question?
Yeah, please.
Okay. First of all, I would like to thank you and the owner of the seminar to accept me and let me join these productive and constructive seminars. I want to ask that.
Can you introduce yourself? Can you introduce yourself?
Yes, I am Ehsan Nedayevskoy from the Institute for Advanced Studies in Basic Science, Iran.
Yes.
I am a physicist here. I'm working as a faculty member of physics department. So I'm not so familiar with, I mean, somehow new in the machine learning concepts, but I'm interested and that's why I'm joining this seminar. So.
Okay, please ask your question.
Okay, thank you. My question is that if I'm understand through from your presentation, you implicitly consider that the noise is a white noise. There is no correlation in the noise. I want to know that if there are some correlation, I mean, the noise is a colored noise and there is some correlation in the noise, can we proceed the same procedure to reach the answers, or something should be else? Should be changed, I mean.
So if you have any idea what the noise is, then it's good because I just gave a formula for it, which so you just need a PDF of the noise. In normally people would do Gaussian noise because then I'm out. So we have to take the log likelihood of that. So it's just L to norm. But if you have a correlated noise, you can put that into the model as well. In that case, it's no problem at all.
Mm-hmm. Yes, because
if you do know the correlations. If you don't, you can put that as a learning parameter as well. I think it should be as well.
Yes, that's exactly what I want to know, because normally we don't know anything about the correlation in the noise.
I think you can.
Okay.
But if you have plus or noise or things that are multiplicative, then it's another story. I'm not sure I would go with that. But if you just have noise which is correlated, like spatially correlated, let's say, then it should be fine.
Okay, thank you.
Are there more questions for the speaker?
Hi, this is Healy from Brown. I'm a postdoc working with George. So I have a very quick question. At the very beginning, you used a retina image to motivate the audience. I'm wondering if you have made any attempt to use the model to study those images, because we are kind of working on these images right now.
No, but I'm looking forward to get applications to work on these things. I'm a methods. I want to work in applications, but unfortunately I don't know much about the problems itself. But that's something I'm looking forward to do. Because one thing is having methods, and I think all these methods, and I also have some methods in tensors that I think are very promising. but you only can show it's something promising if you apply it to data. The problem is that I'm not good at finding data or even like interpreting it. I needed someone to work with me that would
Well, I think he's asking what aspect, never mind what you did, that you have done, what aspect of the retina you're thinking of, because Heli and I have a big project with Harvard Medical School, and we're looking at microaneurysms, for example, and diabetes. But what were you trying to describe with?
It was so to be honest, the retina would not be the best image. What I had in mind was like cancer images, where you think people, for instance, the cancer is evolving over time. So you're taking image of the people over different times, and you can try to model this with a stochastic differential equation. And now the question is this going to evolve to a bad situation or a good situation? You can think as like, is the SDE going to cross some level threshold or not? And now you could like try to learn this with SDEs. This was one of the ideas that we had in mind. And you can also try to model, I don't know, blood vessel movements, and it might not be obvious what is the equations that govern that. And then you have this learning PDE algorithm to try to figure that out. These are some of the ideas, but it's something that once you see the data, you need the data to figure out what you want to.
Okay, I don't want to discourage you, and Heli probably will not tell you that, but I can tell you, please don't try that.
Okay.
It's not appropriate. We do a lot of work with blood vessels and so on, and that's not the law. That's not the laws that you will discover. Okay.
I see. Okay.
Some other applications, yes, but not this domain. I'm sorry to say that.
It's okay. It's good to learn, and it's good to know not to pursue. And as I said, I'm clueless in some of the applications. So, but it's something I look for, is try to validate these methods with application.
So if we have no more questions for the speaker, we can thank both the speakers. So, and with that, we end our seminar today. So thank you, everyone, and have a great weekend ahead.
Thank you for the invitation.
Yeah, thank you, João, and thank you, Simdata. Bye, everyone.